Okay, ladies and gentlemen, it's my great honor and pleasure to start our second keynote session of ICTRI 2023. It's also my great pleasure to introduce our distinguished keynote speaker, Mauro Valatti, who is currently a professor of artificial intelligence at the University of Huddersfield, where he leads AI for urban traffic management and control research team. I is also, like a distinguished scientific person, a senior member of the Association for Computer Machinery and ACM Distinguished Speaker in Artificial Intelligence for the UK. I could have continued listing the achievements by Maura. I would just add, as a final point, that he is a good friend of ICTRI and helped us a lot as a program committee member with thorough reviews for many, many papers. So, Maura, we're happy to welcome you here as our keynote speaker, and please take your floor. The topic of this keynote is the power of good, old-fashioned AI for urban traffic control. I do understand that old-fashioned is rather provocative, because Maura is always at the front end of the traffic control, not in the old-fashioned manner. So thank you very much for accepting this talk, and please take a floor.
Thank you very much, Vadim. You're very, very kind. And I should be now sharing my screen. And one thing that I have to tell you is that I can't see anything but my presentation at the moment. So if there are issues, if you can't hear me, if you can't see me, speak up, and we'll try to fix it. Usually these things tend to break when you need them the most.
Yeah, we'll manage that.
Excellent. Having said that, thank you very much again for the invitation. I mean, as you said, I've been contributing and I've been part of a community of ICTRI for a while, mostly as a program committee member. It has been a pleasure, and I've seen a lot of great works coming through this conference. So it's wonderful to have the opportunity to be here as a speaker to give a different kind of contribution. And as you just said, the title is The Power of Good Old-Fashioned AI for Urban Traffic Control. Slightly provocative, but the idea here that what I want to pass, the message that I want to give you is that right now we are focusing a lot, also thanks to large language models, ChatGPT, a lot of trends which are starting, or which has been started recently on machine learning. And it looks like, particularly for a world outside AI, that these models, these approaches are the solutions for everything. They don't have limits. It's just a matter of optimizing them in the right way. Well, I would like to argue in favor of what is called now old-fashioned AI, which is basically model-based AI. And this talk is to show part of the work that we've been doing with an amazing team of partners. And you can see them at the bottom of these slides. So we had Traffic for Greater Manchester and Kirklees Councils, which are traffic authorities in the UK. We have the Catapult and the UK Orion Innovations, which are supporting us in terms of research grants. And then we have Simplify, which is a company that is working on deploying our techniques in the real world. So that is the overall topic. Before digging into the details of the AI-related aspects, let me give you a kind of overview of why should we care about traffic control and why should we optimize it beyond what is already done. One of the reasons why we need to do that is that because we have a problem, and we have a big problem right now. If we just consider the UK, and I'm doing that because, of course, I'm working in the UK, so I'm more familiar with the environment here, but you can easily translate these numbers, these figures in any other country of the world with similar characteristics. Well, China is well beyond these numbers for a number of reasons. Traffic is creating huge problems. So we have drivers which are wasting a lot of time just in traffic jams. So you are sitting in your car without being able to do anything else. And that is for basically more than a day every year. Congestion comes as a cost, which is the cost of drivers being there. It's the cost of fuel that you're wasting, for instance. It's the cost of fact that goods are not delivered because they are stuck in traffic. And that is 30 billion to the economy of the UK only, again. On top of that, transport is particularly bad in terms of carbon emissions. And transport as a whole, as a field, is the single largest emitting factor of carbon emissions globally. 25% of that comes only from transport. So the problem also from an environmental perspective is huge. Not to mention health. So traffic pollution contributes directly to at least 40,000 premature deaths, again only in the UK. Traffic accidents directly kill 2,000 people. On top of these numbers, which are underestimations, we also have to consider the fact that traffic pollution has a long-term impact on your lungs, and traffic pollution and noises on top of that can have very strong impact on your brain. And there has been works showing direct connections between heavily polluted, heavy traffic areas and a surgence of dementia in people living in there. So we have a problem right now, and it's a big problem, and it's a problem which is affecting us from a number of perspectives. On top of that, things are going to be worse because we have worldwide a city immigration trend, which basically means that the population of the number of people which are living in cities is growing by 1% every year worldwide. So cities are getting larger and larger, which means that the problems which are related to traffic are being exacerbated because you have more people in there, more vehicles going around, of course. And the infrastructure, you cannot expand it, particularly in the areas that you have already built. It is what it is. You can optimize it, but you cannot extend it further. One may argue that we have a number of emerging technologies and techniques, beyond AI, I mean, that can help on that, or that can try to make the problem less consistent. And two elements actually are reshaping the transport area, and has been for a while actually, but we are still to see very real impact. One is mobility as a service, and the clear example is Uber, for instance. Mobility as a service means that you don't need to own a car, because when you need it, it is available for you as any other service. You can call it, it will arrive. It's a smarter version of taxis, if you want. And that, of course, can have an impact, because you can say, well, we will have less private cars because you don't need it. And on top of that, another element that has the potential to reduce the issues related to traffic are connected and autonomous vehicles, and of course, the smart infrastructure that can be put in place in cities. Connected autonomous vehicles means that you don't need to drive them. So first of all, you're not wasting your time in the car. And secondly, they are connected so they can communicate between each other and can communicate with the infrastructure, so they can optimize the way in which they are traveling around. So at the face of it, it looks like these techniques can help us solving part of a problem, because some research which has been done by the KI2Art projects, for instance, says that connected and autonomous vehicles have the potential to improve the throughput of roads more than 100%. So we can have twice the number of vehicles that can go through roads. So we are basically doubling the size of our network without doing anything. And on top of it, we can have improved safety, better service, faster transport. So we are reducing pollution indirectly, and we are reducing, of course, deaths by traffic accidents. These are on the good side. On the bad side, the fact that you have these wealth of vehicles which are available, and the fact that everything will work better, means very likely that people will like to use it more. So travel demand is expected to increase, because why should I work, or why should I take a bus if taking a car is inexpensive and super fast? So you can see that from this perspective, more vehicles can be there. And it is expected an increase in the number of vehicles, and a reduction in multimodal journeys. So again, why should I use a train if I can use a car for similar distance, price is similar, but that's only for me, and it will bring me door to door? These are the kinds of things that should be taken into account. So cutting a long story short, we don't know. We have a problem right now. We believe that there are techniques that can be put in operation to solve the problems, but these very techniques can also make it worse. So we need to act in order to deal with traffic congestion in city. And the way in which you deal with traffic congestion is what is called urban traffic control. And the overall goal of urban traffic control from a traffic engineer's perspective is minimizing delay for all the users of a network. So what you want to do is any vehicle which is in the network is delayed the least as possible. So basically, you are not waiting in queues, you are not waiting at reds in junctions. You have a smooth way to reach your destination. Why do you need to control traffic? Well, two main reasons. One is recurrent congestion, so congestion that happens there every time, every day, peak hour traffic, commuters, for instance. And the second aspect are disruptions, accidents, or unusual congestions. A typical example of unusual congestion are sport events or concerts. These kind of things, they are disrupting the flow, the normal flow of traffic, because you have a huge number of people which are going towards a single place and leaving the single place at the same time. So that has a knockout effect on the network. And then you can have disruptions and accidents. So a car accident in the middle of a road is reducing the capacity, making it hard to move around. Disruptions can be floodings, for instance, can be the fact that you need to do roadworks. Or if you're living in a capital city, might be the fact that you have ambassadors that are going through the city, and you have a convoy of vehicles with police, which is blocking everything to allow the diplomats to pass. And this is having usually quite strong effects on the overall traffic that you need to control. How do you control traffic? So what are the techniques that you can put in operation in urban regions? Well, in an urban region, the only thing that you can really do is optimizing traffic signal phases. So you can optimize traffic lights. What does it mean to optimize traffic signal phases? Well, something like that. You have, let's assume that you have, as in the top left side of this slide, a very easy junction, right? And in this very easy junction, that's a two-way, you can have some number of traffic movements which are legal, and these are numbered from 1 to 8. So these are movements that vehicles can do. What a traffic engineer usually does is create movement phases, so putting together movements that can be allowed at the same time to maximize the throughput of a junction and reduce the possibility of car crashes and accidents. So for instance, in this case, the traffic engineer decided that movement 2 and 6, so the two straight movements, can be together, 1, 5, 3, 7, 4, 8. On the basis of that, you have a cycle. So this is the cycle of phases that can be put in operation in the junction. And when you say you have to optimize traffic signal plans, it basically means that you have to select the duration of each of these phases in order to achieve your goal. So the usual goal, as we said, is to minimize the delay for everyone. So what you try to do, and what techniques which are deployed right now in the world try to do, is to identify the best length of these phases in order to make sure that overall vehicles which are waiting to get through the junction are delayed the least as possible. Okay, that is 40 years of traffic engineering in a single slide. Of course, it is a very high level abstractions, but that at least gives the idea. What is deployed out there? There are three main classes of approaches that can be used or which are deployed there. The largest by far are what is called fixed time traffic lights. Are not responding to traffic situations or traffic conditions. They are there, they have been set with some fixed time durations, and they are repeating these fixed time durations over and over again. They don't know anything about what's going on around them. These are widespread use because they are very cheap. Most of them, particularly for the UK or for the US, they have been put in place in the 80s. They've been set once with two different settings, one for the night and one for the day, usually. And they are there running for decades and decades. And it's quite fun because also traffic authorities, they don't know exactly how they have been set, and they don't know exactly how they work. So when we were interacting with Manchester, for instance, or with the Kirklees Council, which is in charge of Huddersfield, we were looking at maps and say, okay, so how does it work? But can you give me the settings of that specific traffic light? And they were sending out guys with clocks to check the length of the phases, to check the cycles, and to come back to us after a few days to tell us how it was working. So it's not that traffic control also in large cities is completely automated, and it's just a world where you need to find the AI solution that will work. It's a very complicated work where there are things that you can do and there are things that you cannot do. Also, it just for briefly mentioning here, but it's not the topic of this speech. You have engineering aspects that you need to take into account, technical aspects that you can improve. You also have political aspects. So in many capital cities, there are traffic lights that needs to be on green for a very long amount of time because a VIP or a very important person or a president is living or has his residence in a nearby road, and they cannot be delayed because, of course, that is an issue also from a security perspective. These traffic lights are creating huge damages to the general movement of vehicles in the nearby areas, but you cannot control them. Going back to what is deployed in cities, so you have fixed time, which are there, you cannot control, live with it. Then there are junctions which are controlled using what is called reactive methods, so SCOOT and SCATs. These are again from 80s, late 80s, early 90s. And what they do is basically they have small sensors around junctions. They can perceive the movement of vehicles, and on the basis of that, they can slowly react in order to adapt the length of greens and red to what is going on around them. And the last class, which is the least used, are model predictive controls. So model predictive controls are, well, predictive systems that you try to use when you know in advance that something is going to happen. These are typically used when you know in advance that there has to be roadworks or these sport events that we were mentioning before. You can use these predictive systems to simulate how traffic flows will move around, and on the basis of that, you can optimize traffic lights. They can work very well if you have a good understanding or if you have good predictions of how things are going to evolve. They tend to be difficult to be used in real-time applications because they are slow and quite computationally complex. So in this general scenario, AI can play a very interesting role because what we can do and what we try to do is you can have a proactive approach where you can use some part of the power of AI to understand what is going on, decide whether it's likely that issues are going to arise, and then act. And that can be a proactive way. Or you can use it in a fully reactive way, which is more what we will see later on in these slides, saying, okay, I'm using a plugin on an existing system, which is SCOOT, and I'm using AI for better optimizing the way in which traffic lights work. And the last thing about traffic controllers and traffic authorities is just to give you an idea of how traffic authorities operate at the moment in the UK, but similar structures is repeated throughout Europe and in the US. And the daily operations of traffic authorities are, well, you have a division in terms of the roles, and the tasks are divided according to that. So in gray, there are the tasks which are carried on by network monitoring officer. And in green, you have the tasks which are carried on by traffic engineers and control engineers. And this is what you can see here. We'll go in the details in the next slide, but this is the full flow that you follow if something is happening in a network. It's not that you're doing every single step every day, but that is the process that you follow if you realize that something is not going as expected. And the first part of the most intense job, which is performed by network monitoring officers in operating in control rooms, like the one that you can see in this slide, which is the control room of Sheffield in the UK, is that you have these people in rooms, plenty of screens, which are doing their job, which is monitoring how the network is working. And their steps are basically to monitor, identify, investigate, and inform. So they are continuously monitoring the situation of a network. If something doesn't look right, or there is strange congestion which is building up, or something that is not correct, their task is to identify the issue, where it is, investigate, so to understand what is going on, and if they realize that it is a problem that needs to be dealt with, they need then to inform the general public and the traffic engineers. Now, how do you identify and investigate? If you see that something is not right and it's potentially wrong, you check whether you have CCTV cameras that can look at the specific area that you want to check. If you don't, you call bus drivers, taxi drivers, tram drivers, anyone which is which can provide you eyes on the scene, you call and you check in order to get descriptions. If still it's quite unclear what's going on, you send officers that can tell you what's going on, and you call the police, and you make sure that you can perfectly understand the problem. Once the problem is understood, the ball moves into the pitch of the traffic engineers. The work of the traffic engineers is in a much more, let's call it a relaxed environment, if you like, which is something, it's a usual meeting room. So what they do is, okay, there is a problem, and they have been informed by this problem by network monitoring officers. So their tasks are to verify the issue, evaluate what can be done, if something needs to be done, implement the solution, inform the general public and the traffic authorities or any stakeholder which is involved, and then control that the solution is working as expected. In many cases, what you actually do is that you are printing down maps of the area that you are controlling. On the basis of these maps, you understand the extent of the issue and how large is the area which is going to be affected, whether the problem is going to solve itself by night, for instance, if it is a traffic accident, a few hours, and hopefully it will be gone, or whether it's a more significant issue, and then you need to put in operation mitigating actions in order to deal with that. It's extremely important also to know that, well, most of the issues, if they are temporary, they are solved by night because there are less vehicles. On the other hand, if you need to put in operation a solution, if you need to implement a mitigation strategy, then you are legally responsible for the issues that this mitigation strategy will create. If a traffic accident happens, insurance companies, the first thing that they will do is sue traffic authorities because something was different than usual, and that can have an impact on the way in which traffic moves, of course. So traffic engineers are very careful to decide whether there is a need to implement something, and that can be justified legally, or whether it's better to let it go, let things evolve by themselves. It's a kind of a grim picture, I understand, but that's the kind of world where you need to work if you want to work in traffic control. And so we get so far in terms of a description of the environment where we are looking for this good old-fashioned AI to be active and to operate. Which class of good old-fashioned AI are we speaking about? Well, that is AI planning. So what is AI planning, and why is it good old-fashioned AI? So AI planning, I just pick up some quotes from extremely distinguished researchers in the field, like Patrick Asbom, Jörg Hoffman. And the idea of planning is basically, in a nutshell, selecting a course of actions, so a number of actions that allows you from an initial state to reach a goal state that you like in the world. If we are translating this in a traffic environment, this means I want to operate on the network in order to allow the traffic issue to be resolved. Actions that you can do are you change traffic light settings, for instance. That's just for giving an idea, and that's how we use planning in this scenario. And in terms of an overview of planning, why is it good old-fashioned AI? Because it is model-based AI. So what you do is you have a knowledge model that can be represented in PDDL, for instance, which is one of the standard languages for planning, where PDDL stands for Planning Domain Description Language. There are different versions of it. You describe in this language the problem that you want to be solved and what you can do to solve it. You pass this knowledge to an automated solver that can be called the planning engine that will hopefully find for you a solution, which is this sequence of actions, which is telling you, okay, at this time you need to do this, then this, then this, then this, and this will allow you to reach your goal. Providing a slightly different perspective, what it looks like is something like that. So you have on the left-hand side the knowledge model, which is provided. In the center of these slides, you have a planning engine, and on the right-hand side, you have the solutions that you want to be generated. Now, when we're speaking about PDDL specifically, the knowledge models are in fact two. One, which is called the domain model, top one here, and the other one, which is called the problem model. Why is it doing like that? Because, well, that is for standardized reasons and tradition, actually. So this language comes from the 90s as well. And the domain model includes general knowledge about the application domain that you want to be solved. So for instance, if we are speaking about traffic control, general knowledge is the fact that you can change traffic light durations within some constraints, and cycles must remain the same. And when you have two roads which are reaching each other, that is a junction, that sort of general knowledge. While the problem includes specific knowledge for the instance that you want to be solved now. It's like a snapshot of the network in this specific moment. So the structure of the network, where the vehicles are, and so on and so forth. Sorry. You provide this knowledge and this model to the planning engine. What the state-of-the-art planning engine does is they create search space, which is a graph, that is then explored on the basis of a heuristic, which is just a compass that you use to explore the search space. And that will hopefully guide you to a goal state, and this path from the initial state to the goal state is your solution, and it's exactly a sequence of actions that can be provided as output, as on the right-hand side. And so you have this sequence that is what you need to implement in the real world or in your domain of interest in order to make sure that your goal is reached. This is an oversimplification. It's just providing you an overview of the field. Again, by no means I'm claiming that I can concisely describe decades of research in the area, but at least we know that there are models, there are reasoners, and there are hopefully solutions. And the language which has been used by us for this work on traffic control is PDDL+. So PDDL+ is the most expressive in the families of PDDL languages, and it allows you to deal with hybrid, discrete, and continuous problems. Discrete and continuous means that you can represent the fact that changes are continuous over time and changes are discrete. So there are things that happens instantly, or where you know exactly what is the duration, and there are things that has a continuous flow that you can deal with. And this PDDL+ allows you to deal with problems where both these perspectives, where both these aspects need to be taken into account. And it does that on the basis of three main constructs, which are part of a language: actions, processes, and events. What are the differences? Actions are what you as an agent, which is trying to solve a problem, can do. So this is your impact on the world. And actions are described in terms of preconditions and effects. Preconditions means that you can apply the action only if the preconditions are met. Like you can pick up an object only if your hand is free and the object is on the table near you, right? Otherwise, you cannot pick it up. And the effects are a description of how your action is changing the world. If I picked up the object, the effect is that the object is in my hand and the object is not anymore on the table, and my hand is not free anymore for other objects, for instance. That is, again, very high-level description. These actions represent what you can do. Processes and events in PDDL+ are used to represent what is going on in the world. And these are basically the way in which the environment is reacting to what you are doing. And the main difference between them, is that processes represent continuous changes in the world, and events represent instantaneous changes in the world. Their structure is similar to that of actions, so you have preconditions and effect. The only difference is that since they are not under your control, they are triggered or executed as soon as their preconditions are met. So their use allows the environment to evolve even if you are not doing anything. Basically, these PDDL+ models are simulation models because you can simulate the natural evolution of an environment even if you're not acting on top of it, or also if you are acting on top of it. So the use of this language makes it, well, it's very good in environments which are dynamic, of course, but it makes it a bit harder from a planning engine perspective to deal with it, because it's not a matter of identifying a sequence of actions in a static world, so where you know exactly what is going on and you know exactly how to deal with it, but you need to anticipate the way in which the world is evolving, and you need to understand how to act on top of it in order to make sure that your goals are reached at some point. And a very high-level example, just to give you, again, a part of the syntax of this language, is in a didactical example that we use for showing this language for the first time. A typical case where you can use processes and events are if you want to simulate a world where you need to control a ball. You have a ball in your hand and you can let the ball go, and the ball can hit the floor or the ground or the table and bounce back. And what you need to do is to let it go, let it bounce once or twice, and then try to catch it again. That is usually an application of planning in robotics, where you need to understand where the ball is likely to go and how you're moving your arm in order to catch it. And this is a very good example of discrete, hybrid, and continuous, hybrid, discrete, and continuous cases, because the fact that the ball is falling can be nicely represented by a process. And this is a continuous change because the position of the ball keeps changing over time in a continuous way. As soon as the ball hit the floor or the ground, it's bouncing back. That hitting is something that you can represent as a discrete change in the world, and you can nicely represent this as an event, which is basically switching the direction of the movement of the ball and changing slightly the dynamic of the processes, which is controlling the way in which the ball moves. And on top of that, you can have the actions, and an action here can be just the fact that you are dropping this ball. So you are starting these flows of processes and events. You are starting actually the simulation of a world. And now that we have seen basically, what is traffic control? Why do we need to deal with that? What are the usual conditions where we need to operate? And what is the mean that we have decided to use? That is that planning that gives us this goal-directed way to solve problems in the world in an hybrid fashion. How do we use it in urban traffic control? Now, the idea for us was to say, okay, in recurrent traffic conditions, so commuters and morning or evening peak hours, there isn't a very strong need for this class of approaches because the techniques which are implemented, so the Scoot system, is generally working quite well for this traditional situation. Where it doesn't work well are when you have these unexpected events or undesired traffic conditions. So something which is slightly outside the common pattern of movement in cities. And when something like that is captured through monitoring, we can create a problem that we want to be solved. So there is an issue, we identify the issue, we create a planning problem to be solved, we execute a planning engine. This planning engine likely, and we have seen in part of our empirical analysis, create a solution quickly, and this solution can then be deployed and implemented in the real world in order to address that traffic issue that we have identified. And the structure on which we are working right now in an area in Huddersfield. So you can see in the picture there is the usual glorious UK weather, and that is an actual picture that was taken in June of Huddersfield. And the buildings that you can see in the backgrounds are part of a university campus. And this road is one of the main roads. I'll show you later in a map, but this is one of the main roads that can connect the Huddersfield town with Wakefield and some other cities and the motorway. So it's a major corridor for the town. In this major corridor, there are a number of junctions, and you can see one here just at the bottom of the picture. You may have an hint at the back of it, but there is a selection of 6 or 7 junctions on approximately 1.5 kilometers. And on these junctions, there is that SCUD system that I was mentioning before in operation. SCUD system is in operation, so there is its own sensors which are available and its own controllers which are in there. The idea, the way in which we are using AI here, and planning in particular, is by creating a plugin that you can turn on and turn off in a specific region in order to take control of what is going on, or to take it off and let the usual SCUD system work in your place. So you rely on the sensors which are available, you rely on data which is available, so you minimize costs for traffic authorities because you don't need additional hardware, but it's only a software matter, and you turn it on and off whenever you need it. Two things which are important, and that will be highlighted also later on in this talk, is the fact that if you have a knowledge model, in particular if you have a PDDL plus knowledge model, you can solve problems, and that's one of the main reasons why we are doing that, but you can also simulate what is going on and what is likely to happen in the future. Simulators are extremely expensive for traffic authorities because there are few which are relatable, and their licensing costs quite a lot, and they require a lot of time from experts in order to create models which are reliable. So if you can provide a simulator almost for free, even if it is not extremely accurate, that is already a significant step forward. And that is one of the very strengths of this good old-fashioned AI. You have a model that you can check and you can look at if needed. And the idea of this then overall infrastructure is that once you have created the solution, you are implementing it back if you want, you are simulating it if you prefer, or you are just throwing it away because maybe it doesn't work anymore, or the situation has evolved so quickly that you don't need anymore. You don't need it anymore. What are the kind of information that you are collecting? So from this system, you need, of course, dynamic data that tells you, okay, exactly in this precise moment in the world, in that area, what's going on. And you need to have also static data that you need to collect. So static data are on the left-hand side, dynamic data is on the right-hand side. So static data is, of course, the topology of the area that you are controlling, where topology also means capacity of the roads. So how big are the roads? How many lanes? How many vehicles can they accommodate? What are the junctions, and what are the traffic signal positions? And also what are the settings of these traffic signals in terms of phases which has been designed, and the overall cycle, and constraints in terms of minimum and maximum time that you can give to each phase. Now, if you recall from one of the very early slides in this talk, you have the phases and then you have the cycles. Constraints are put on both of them. So for each phase, you have a minimum and a maximum time, where the minimum time must be above, I don't remember, whether 10 seconds or something like that, because you need to hold the cars the time to start their engine and start moving. And the maximum time is set for each phase and for the overall cycles in order to avoid unexpected behaviors. Because, for instance, if you let people wait, pedestrians mostly, at a traffic light for more than 2 minutes, they will start cross anyway, because they will believe that the system is broken and the traffic light is not working anymore. So you need to be very careful when you're dealing with these constraints on the length. On top of phases that I mentioned before, there are also intergreen timings. These are used not everywhere, but in some countries, particularly in the UK, they are used, and these are period of times where basically all the traffic lights of a junction are on red, in order to allow the junction to discharge vehicles that maybe were stuck in the middle of it, waiting for their opportunity to cross the junction. So you also can have intergreens in between of that. And the last bit of static knowledge that you need are the permitted traffic movements. So how vehicles can move around in your network, in which directions, for the links and for the junction. When it comes then to the dynamic side of the data, there is a snapshot of what is going on right now, or a snapshot of what you'd expect to be going on in a moment in the future when you will be implementing the solutions. So what you need to know is the occupancy of the links, how many vehicles are there for each road, the state of all the junctions in terms of what traffic light is on green, for how long, what has just been executed as a cycle. And the other bit, which is a bit more complicated, is average traffic flows. So for each junction, how vehicles are moving around on average at this specific time of the day. This average traffic flow is quite complicated because it embodies two different elements. First of all, how many vehicles are there? And second, and the more subtle aspect, is the intention of traffic. Because you may have that for a specific road, during the morning, basically all vehicles are just going straight because they are going to their offices or whatever. And then during lunch, when there are lunch breaks, you have many vehicles which are turning right or left because maybe they are going to some restaurants or to some shopping malls area, which are positioned there. So these average traffic flows embodies the two different souls of vehicles moving through a junction. And the last bit, that can be a bonus, so it's a very nice plus to have, but it might not be available at the time of planning, is the fact that you know the way in which the unusual circumstances are affecting the control region. If you have a car accident in a link, how is this car accident reducing the capacity of a link? Is it blocking a single lane, two lane? Is it blocking the whole link? This information might not be available, in many cases it is not, but it's a very nice plus if you can incorporate that as well. And how did we take this knowledge, or take this information and created our PDDL Plus model? So processes, so these constructs, which allows you to represent continuous changes, have been used for describing flows of vehicles and modeling green time. So basically for us, vehicles are something like water, if you like. It's a bit of a stretch, that I understand. But if you consider the kind of metaphor that we are using here is waters and tap. When you put on green on a link, you are basically opening a tap and you are allowing water to flow. And that is the same that we try to do when we consider traffic. When you put on green a traffic signal, you are allowing vehicles to go through. And so the process represents these flows of the vehicles. Events are used to control limits. You reach the maximum green time, or a link is full, so it cannot accept any more vehicles, or a link is completely empty, so you cannot have a flow of vehicles going out of it because there are no vehicles. And the only action which is under the control of the planning system is the fact that you can change or that you can stop a phase that is running right now and move to the next one for each of the junctions which are under your control. I forgot to mention before, but I think it should have come through quite clear, that we are using in this case a centralized approach. So we have a single planning system which is in charge of a network and which is controlling every junction in order to make sure that the whole network performs well. And well, I don't think this was, again, just for showing a slightly part of a syntax that can be used. And in this case, these are part of the information that needs to be collected in order to have a problem model that you can deal with. So you can see, for instance, that you need to describe, as we were saying before, what is the status of a junction, so which phase or stage is active, for how long it has been there, what is the sequence of these phases, and whether or not you can control the junction, because you may have junctions that you can model, that you need to model, but you cannot control. Then we have the average traffic flows. So these turn rates are the aspects that incorporate the intention of the traffic and the amount of traffic which is on the road at the same time, constraints on the length of the phases, and then the current occupancy of the road, how many vehicles are there, and the maximum size of the road. And then, of course, you can also specify a goal if you like that. Well, you need to. And in terms of components of these domain models, in terms of structures, that is, again, an expert that includes part of the constructs which are in there in terms of processes and in terms of events. So as we said before, the processes are used to model vehicles moving through the network, and that is exactly the case of this flow run green. And cutting a long story short, what this flow run green is basically allowing vehicles to leave one link and join the next one if there is a corresponding legal traffic movement that is connecting these two links through a specific junction. The keep green process is just used for making sure that we are counting for how long we are letting phases on green. And then we have events that are doing this control of limits. The only action which is in here is that this is one of the early versions of the models, and it's also one which is slightly easier to describe than the one that we have in operation at the moment, which has been extended and enhanced on the basis of the feedback that we were receiving from traffic authorities. And this is the only action which is in there. And these actions allows the planning engine to say, okay, through this simulation, right now we are expecting to have a specific phase on a junction on green. If I can control it, and if I want it, I want to have the power to stop it right now and to move to the next one. So this is a means that allows you to dynamically decide the length of phases which are running. And the planner can do that for each phase, of course, and for all the junctions which are under its direct control. And in this way, you are performing this very dynamic optimization of the junctions while keeping an overview of a network which is under your control. What about the goals that you can set? Well, on the one hand, the single goal that traffic engineers work towards, that was, as we mentioned in some of the very early slides, is to minimize the delay for every vehicle in the network. It's extremely hard to represent in terms of a symbolic knowledge. So we try to keep things easy, and we try to find translations of what does it mean to minimize the delays for vehicles. Well, on the one hand, if you have congestion, what you want to do, or what you are aiming at, is allowing vehicles to move through your network as quickly as possible, within legal limits, of course. We're not firing vehicles through a corridor at maximum speed. This basically means that where you can either require a very high or a high number of vehicles to leave your area through a given exit point, because we can represent enter point and exit points. And so you can say, okay, this is a single corridor. I want vehicles to navigate through the corridor. So my goal is to have many vehicles as soon as possible by the end of it, which means I'm minimizing their delays because they get to the end as soon as possible. Or if I know that there is a single link which is particularly congested, the goal of minimizing the average delay for everyone can be translating in reducing as soon as possible the number of vehicles which are on that link, so that they are not waiting, and so that the average delay for everyone drops immediately. There can be more complicated goals, of course, but we decided that, well, in concert with the traffic authorities, we decided that these cast of goals were enough to start with some trials and to have some initial results that can be shown and that can be put in operation. The last aspect that you need to consider, so we are focused a bit on the knowledge models. There is also another aspect that you need to consider, which is the planning engine. How does it work? What are heuristics and search that we want to use? We drop any requirements in terms of optimality, and that I think happens quite often in real-world applications, because, well, real-world and optimality, they are usually at a clash. And particularly in this case, when you are relying on simulations of something that is extremely unpredictable as traffic, because even if you have an extremely accurate simulator, there are so many things that can happen in network that can block it. It can be a bus which is stopped in the wrong way, or a car accident, a dog which is crossing the road and every car is blocking. So forget about optimality. We decided to go for something which is quick and dirty, so greedy best first search. And we also devised some specific heuristics that can deal with a class of problems that we are working on. And this class of heuristic is focusing on the idea that we abstract away the actual structure of the junctions. We assume that vehicles can always cross the junction at a given average rate. And this average rate is calculated on the basis of the current setting of a traffic light. And on the basis of that, we are significantly simplifying the problem, and we can find solutions in a very limited amount of time, which is basically what we would need to do. Details of many of the things that I'm saying can actually be found in the papers that we publish, and I've put at the bottom of the slides the reference, well, a very short reference to the corresponding paper that I'm referring to, and at the last slide, I have a list of publications. So, of course, right now I'm giving you an overview, but if you are interested, well, get in contact with me or check the publication list. And how does a solution look like? We have seen that the solution is a sequence of actions, and in this case, it's a sequence of when you want to stop a phase that is running at a given time. So basically, if we want to have an interpretation of the solution plan is telling you that after 5 seconds, you have to stop the phase which is active on junction N180 whatever, and move to the next one. And after 65 seconds, you have to switch quite a large number of phases for a number of junctions, and so on and so forth. What do you do with the plan? In the infrastructure that we have seen before, this plan needs to be sent to the controller of the specific junction. And these gray boxes that you can see near junctions or near traffic lights are the controllers. So what we do in the infrastructure, where we use the AI as a plugin, is this plan, of course, translated and made in a way which is digestible for the system which is running in that controllers, is sent to them, and the controller is then putting them in operation in the real world. There are some caveats, but we can discuss them later if you want. And did our approach work? Well, on average, in simulation, of course, we have observed a 20% improvement in delay reduction and in emission reduction. Now, emission reduction is a very nice plus to have in terms of performance, because we are not directly modeling emissions. So this goal or this reduction comes as an implicit general improvement of the way in which vehicles are moving. So it's a kind of byproduct. We cannot directly control it, but by improving the flows, you are also reducing pollution overall. And in terms of how fast can we generate solutions with planners, that is a matter of seconds. We have seen that in easy-ish cases, it can be below a second. In a bit more complicated cases, we can get to 10, 15 seconds, which is still extremely acceptable if you consider that traffic engineers take hours or days in order to create a plan that can be put in operation. Of course, we are comparing against humans, so it's not completely fair to do this kind of comparison in terms of runtime, but it is what it is. And I've been talking a bit about, complexity of the problems. And since we are taking a centralized approach, you may ask, does it scale at all, Mauro? It's very nice. You can control a lot of junctions. How many of them can you control? Well, we started easy. So that was back in 2012, something around that, where we had some of the first trials which were run in simulation, that was Sumo, on a small network with just 3 junctions. And basically here, the point was just to check whether by changing the duration of traffic lights, we were able to balance the overall control of the network. Then after that, we moved on something a bit more complicated, well, significantly more complicated than that Sumo. And that was, again in simulation, using AimSum, on an area of Manchester. And you can see, I hope you can see here the general Manchester area. And Manchester is structured basically in two ring roads. You have the inner ring road and the outer one. And this area, which is shown in the main picture, is the corridor that connects these two ring roads. So it's a very significant area and a very complicated one to control. And we were able to control it. There were some 7 different junctions with very complicated, from the point of view of the phases and the traffic flows, junctions that you need to control. And then we moved to a more extensive area. It's again Manchester, a different map. But well, if you like football, you may know that long corridor here, because at the end of that, there is the Old Trafford, which is the home of Manchester United. And so we extend the area that we were controlling before in this picture here is this small rectangular area. And so there is an extension by 3-4 times in terms of junctions that you can control. And this is one of those where you take some 15 seconds in order to create solutions to some of the problems. But it can scale up. And this is the area that we are controlling at the moment, where we have been doing some trials in the past few weeks. And it's the corridor which is connecting, as I was mentioning before, Huddersfield to Wakefield and to some motorways. And the area that we control is actually the whole corridor, which starts here from the junction with the Ring Road up to this shopping mall, which is the Morrison down there. And this, it might seem quite easy compared to others because it's a single corridor. But on the other hand, that creates a lot of complicated interplay between the junctions which are in there, because you cannot let traffic dissipate through the network, but you must make sure that it goes through this corridor as quickly as possible, regardless of the issues that you're facing in terms of congestions. And what next in terms of how do we want to extend the area that we are controlling at the moment? So there is the whole Kirklees region, which is under the control of the Kirklees Council Authority. The corridor that we are looking at the moment is the one that you can see just next to Huddersfield. And what we are doing now with the Traffic Authority is to extend the area that we can control to the whole region. By no means we expect a single planning system to be in charge of the whole area, but we would try to break it down in critical areas that can basically be controlled by a single agent, and have a kind of a hierarchical way in which areas are merged together, and there is an agent on top of it that can decide whether there is the need to apply some modifications or not. But that is what is next for us and what is the future of what we want to do. So far, I've been describing the techniques that we have designed. I'm quite excited, of course, about the AI planning side, about the results that we got, so the 20% improvement that can be achieved. I didn't really tell you anything about the benefits of good old-fashioned AI or model-based AI. Why are we pushing it so hard in this specific field? Now, let me try to convince you, and I'm quite sure that some of the points raised here will potentially bring up some questions, and that's exactly a part of the reason for this talk. So let us discuss, let us reflect on this class of approaches that seems to have been forgotten by someone. So, remark again made before, you have a simulator for free. All that knowledge that you are encoding in your symbolic model, and in this case, in the PDTL Plus model, is a simulator that you can use first-hand for creating solution. Second, for simulating data that you have in your record, historical data. And third, to perform what-if scenario analysis, so that you can try in simulation different approaches. You can demonstrate on the basis of your simulation that they work, and so you can take a more informed decision. And this simulator is also a tool that you can use to interact with experts to show why you believe that the plan that has been generated is a good one, and what do you expect to happen, and what would happen if you put in operation a different one. And the core, of course, of this good old-fashioned AI are the knowledge models. So everything that you need in order to reason, in order to create solutions and to create strategies, is encapsulated in these knowledge models. This means that you have overall control on that model. So you can update the model if circumstances change, and that's what we are doing. So we started with a rather not simplistic, but rather intuitive model that I've been showing you, and then through interaction with experts, we modified it in order to make sure that it was, first of all, deployable in the real world, and second, it was reflecting their understanding of traffic control. And there is no need to create a single model. You can have multiple models that you can use for different needs. And in fact, in this infrastructure that we are using for simulating different scenarios, we have one model which is extremely accurate that is used for the simulation of how we expect traffic to work. And we have another model which is slightly more abstract, that makes the computational complexity easier, that is used for creating quickly solutions. And of course, there is no limit to the number of models that you can generate according to the needs that you have in your specific applications. And the model itself can play a role in the documentation for the application. You can specify, well, you can document and specify on the basis of the model what is your understanding, or what is the understanding of how things can be controlled, what are the constraints, what are preconditions, effects, etc., etc. And that, again, is a very useful tool to discuss with experts, but also, in the case in which you are going to face legal charges, to describe or to show that everything which was under the control of a system was perfectly fine in terms of the constraints which has been defined. And so it was legally valid, let's put it with. Another reason why models are pretty good, so that was more on the documentation, interaction, generation side. Another reason why models are particularly good and why you can use, and why they can be a viable mean for creating solution, is that you can reformulate them either inside the same language, and in planning, for instance, we have these things which are called macro actions or action splitting schema, where you are taking these models in this specific language and you are changing it in ways where you know they will be less easy to be read by humans, but easier to be dealt with by automated reasoners. And you can change that inside the same language or in a different language of the same family. On the other hand, you can also take that same knowledge model and translate it into different formalism, of course, within the same complexity class, because otherwise that can be quite difficult. But you can then unlock the possibility to use a wider range of solvers. So from planning, you can easily translate your problem to SAT or max SAT, according to what you want to solve, ASP, CSP, other classes. So the models allows you to exploit a wider pool of solvers beyond those that simply accept the language in which you have written the model. And of course, the model is the single point of contact where you can look at it, document it, discuss on top of it. The other aspect, which is again, of course, related to the model itself, is that with model-based AI, it's much easier to perform verification and validation. So the knowledge models, of course, are symbolic models. They must be formally correct. You have a syntax to follow. You have a semantic which is well defined. And what you can do then is, first of all, verify them against the requirements, right? And again, that is very good from a point of view of legal issues that you may face. And basically, as in any software engineering approach, you can perform, and there are approaches where you can perform this kind of verification. You can also validate the models, the general model itself. You can validate the solutions in simulations, but also against the model, in order to make sure that some legal requirements are satisfied. And again, this validation may be run against different classes of models in order to make sure that even if you have created your solution with a model which is slightly more abstract, in order to make the computational complexity low, a number of other aspects that you need to take into account are encapsulated in that, and you can formally prove it via validation. And the last point, which is again quite interesting, is that you can check correctness of the input that you are provided. So what you can do is, and what we have been doing, and we've identified a number of issues, is that you create your model on the base of the dynamic data that you are pulling from your sensors. And these models give these knowledge allows you to create that snapshot of what is going on in the region at this moment, and you can check that the data that you have pulled is correct against the model. So you can check whether it is correct that that specific traffic light is on green and has been on green for this amount of time or not, where it's correct that this specific traffic light is on this phase instead of this other phase, and so on and so forth. And actually, in the work that we have done, we were able to identify in several cases that some sensors were broken or were disconnected from a network, and they were not providing correct information, but the system which was deployed, so the SCUT system, was reacting to data which was faulty. So again, that is something that can come, of course, at the cost, but can come quite easily and quite handful when you have a knowledge model that you can dig into and that you can exploit. And the last thing is, well, I started this talk saying that I wanted to show you something, or I wanted to let us reflect on a class of approaches which is not as trendy as large language models, ChatGPT or whatever. And then I find myself using one of these buzzwords and keywords like explainable or explainability. But in fact, it is true. So with knowledge models and with model-based AI, you have a mean in which you can, if not to fully explain a behavior, you have a mean in which you can try to find the ways to provide suitable explanations for what is going on. So if you have, since you have this planning engine, which is performing the reasoning process for you, for creating solutions by exploring the search space, you can do reverse engineering and understand why a specific path has been taken. Of course, general answers will not be at the satisfaction of domain experts, because the fact that one heuristic is preferring this node over the next node is not an excellent explanation for most of the cases, but it can be the basis on which you refine your tools and techniques, or on which you create better explanations which are at the level of what would be expected by human operators. The fact that you are relying on models and on reasoners means also that you can perform that what-if scenario evaluation. So you have a simulator underneath, and you can test different opportunities in order to show, well, this plan which has been generated is better than the other one for this reason. We run it again, and we show it to you. And of course, there are then these general questions about explainability. Why did the system do that? Why isn't it able to do something different? Why is what the system proposed more efficient than something else? These are all questions that in some way you can answer using reasoners and knowledge models. I'm not arguing in favor of the fact that answers will be easy to understand for everyone, but you can have answers and you can build on top of it something that makes it easier for domain expert to understand. And yeah, so before moving into that, what I want to tell you is also that, okay, the focus here has been on the automated generation of traffic control strategies. We are also using planning or model-based techniques for other kind of approaches or other kind of application in traffic control. And one is for traffic routing via connected autonomous vehicles, where you can communicate with the vehicle and you can tell the vehicle the best route to take in order to distribute traffic. We are working also on intelligent public transport systems, and so where we can basically customize bus systems, where you try to optimize the way in which the bus timetables are working in order to make sure that you are satisfying the demand of passengers, and in station train dispatching, so the way in which trains move inside a train station. So that's the larger portfolio of approaches and domains where we're working on with planning. And for giving a kind of conclusions of this talk, which was, I understand it was quite a wide ride. And what I wanted to show you is an example where model-based AI, and in particular planning, has been applied to improve current practice. And I wanted also to provide you an highlight of old-fashioned AI benefits. What they can provide in a nutshell are decision support, where you can interact with the system and better understand why the decisions have been suggested, possibility to simulate complex scenarios, and possibility to update and maintain the knowledge without the need to retrain or to identify more data and to check the data, etc., etc. If and when you want to use planning, domain-independent planning, which is the class that I've been focusing on today, is very well positioned for quick prototyping and testing of solutions, approaching sees if that class or techniques can work for you. And well, that is basically allowing us to tell that good old-fashioned AI is not out of fashion yet, and that's something that I hope came through this talk. The very last point is that I may have presented this as it was my own work, just by myself. There is a large team of people which has been collaborating and which has been contributing in different ways to the work that we've done, and I just wanted to list them here in order to make sure that they get their proper recognition. Here is the list of pointers to the papers. I think that I can send it to Vadim, or I can make it available to you if you're interested. And I'll stop it here in order to allow you to make some questions and not to delay your lunch break. Thank you very much.
Thank you very much, Maura. That was an exciting talk. It just stimulated to push you back even to an older-fashioned and great AI. But I would like to offer the panel to pose their questions first. Are there any questions in the audience, please? Okay, just to kickstart the process, after mentioning that if you wish to ask anything, just raise your hand in the interface, please. I will start with pushing you retrospectively back to the 90s, Mara. So just imagine that we look at the scenarios of distributed planning for distributed plans. So it's a sort of peer-to-peer multi-agent system which you can easily imagine. Would that help you scale?
That's an excellent point, actually. And one thing that I didn't mention is that, of course, we are taking this very centralized approach to traffic control because we want to tackle a situation where unexpected issues happen. And so in this case, we believe that controlling the whole network in a single agent fashion would be helpful. There are other techniques like Surtrack, which has been developed by colleagues in Carnegie Mellon University, where they are taking exactly a multi-agent approach. And it's based again on not planning but scheduling. So they have a knowledge model, but instead of having a single agent which is in charge of the whole network, you have an agent per junction, and they take local decisions and communicate with each other in order to make, in order to allow you to scale and to allow you to deal with a wider region. They work very well, they scale very well, they serve a slightly different mean. So they wouldn't work on completely unexpected situation or unusual events because they tend to react a bit slower than what you can do in a centralized fashion. But by no means that means that they are not good. They are very good, and they can control much larger regions than what we can in a centralized one, of course.
Then we will start moving slowly forward to the present and just recall ourselves about the coordination strategies like people did for electricity distribution networks, for instance, Did you consider this approach to make an hierarchical coordination system for small areas, for proximities, small areas, bigger areas, like metropolitans?
We are thinking about that, yes. That last step that I've shown where we are moving towards much larger regions, it's something where we are starting to work right now. So that is the moment in which we are looking at the different techniques that we can put in place in this hierarchy of agents. And the main question actually which we are working right now is what is the right size of an area to have this wonderful trade-off between I am controlling all the region where I believe that some traffic congestion issue can have an impact, and I'm not stretching my system too far where we're reaching its boundaries in terms of capabilities. But after that, we will look into what can be used in order to ensure the coordination of systems, because that is a core in that class of approaches.
Does this recall you the in-layers in deep learning models? Or resemble a little bit?
That recalls me slightly more of a hierarchical task planning, actually, where.
That's as well. So,
but yeah, there is of course similarities with that.
I will offer you to move forward again and just recall about the rise of the tide of sensors in the networks. And just imagine that an agent sitting in the proximity of a junction have got access to global positioning data in the proximity, in addition to the camera video which is installed at the junction. Would that be helpful?
Yeah, and we are absolutely looking into that. So part of some of the projects that we've been working on, and one of the projects we are collaborating right now with Manchester, is saying, okay, at the moment, as you're saying, we have a huge amount of data that can be collected. So the Scoot system only relies on pressure data. So you have a pressure sensor on the road, while what is available in Manchester are pressure data, Bluetooth data, GPS positioning, well, counters of GPS positioning, and CCTV cameras that can tell you not only how many vehicles are going through, but what are the characteristics of this vehicle. Are they van? Are they bikes? And so on and so forth. So we are looking into that in order to extract an enhanced knowledge that can be incorporated in our models to make better decisions.
It just recalled me suddenly a viral video taken on London Bridge when a person with a tray containing 3 dozens of handies passed through the bridge, and this immediately resulted in the data splash showing the jam there. Would these situations be verified using your approach? You mentioned the verification of this data.
If that is a very good question, and it depends on which data are available for that region. If you only had that data, your system will be tricked in believing that there are a lot of people on the phone, and so there is a lot of traffic. If you have other sources of data, like the pressure sensors, you will have a clash between the different sensors, and so that will raise a flag and saying there is something wrong. We don't know what it is, but better to look into it.
Okay, perhaps finally, just to give some floors to some other people, what if we consider putting game theoretical approaches for coordinating these hierarchical layers in the control system? Would that be feasible to do?
That can be something quite good, actually. We didn't explicitly look into that, mostly, I guess, because we don't have much expertise in game theory. And we started with this planning side, and it seems to be working fairly well. But that's definitely something to explore more.
Yeah, it could be interesting to investigate whether it's possible to use auctioning strategies, for instance, for coordination.
Yeah.
I see one raised hand. It's Vitaly Kobets. Please take a floor and pose a question. Vitaly?
Thank you so much for this possibility, and thanks a lot for your very applied investigation and very interesting research. And I have one question. Could you please to tell what are the limitations of your model, for example, to achieve traffic goals? Maybe which threshold exists during your simulation or something else?
No, that's a very good question, actually. So, in terms of the limitations, well, one limitations, which was also mentioned by Vadim before, is that the size of the network that you are controlling. So, there is a limit of how many junctions you can put in there. Otherwise, simply you don't have enough computational capabilities to deal with that. Other limitations are the fact that since it's not really a limitation of this approach, but it's a limitation in general of the field, is that since you are working in simulation and you are basically predicting the future, if the future is very different from what you are predicting, and your plans will not work. And an example what we have seen, if you consider areas where you have single lane roads, for instance, you can make all the simulations that you want and you can try to create a plan that works very well. But if you have a car which is struggling to park there, it will block you completely. And there isn't anything that you can do on top of it. So, cutting a long story short, you can have models which are as accurate as you want, but the real world will block you from doing things which are too smart or too much into the future. And we try to make plans. We investigated empirically what was the reasonable time horizon to consider for the plans. And we have seen that something around 10 and 15 minutes in the future, that is around the maximum where you can plan in advance. Beyond that, it's sci-fi. Below that, it's very good, but it's too short as a time window. So 10, 15 minutes in the future, that is it.
Thank you so much. Thanks.
To have more questions, Maxim Volashuk, please.
Firstly, I want to thank you for your speech and ask more single question about what was your motivation of the starting of the investigation about this model of traffic jam, traffic moderation, and if the why did you choose to use AI models but not some deterministic algorithms for that reason?
Okay, that's a very good question, and I think that usually the answer to this question are not as exciting as they should be. So in our case, in my specific case, we were involved in a European network where they were bringing together experts from different disciplines in order to try to find collaborations for solving traffic problems. So I happened to be there. I happened to have experience together with colleagues from my university in planning. And by discussing with traffic engineer experts, we said, okay, this fact that planning is goal-oriented, so the fact that you can specify a goal and you can create solutions to achieve this goal, and they are timed in terms of the plan tell you when to do what, seems to work quite well because you have a language to say, okay, the ideal condition of a network is this one, and that is my goal. A solution to that is this sequence of actions, and that starts to be a ground to discuss with engineers about what we are planning to do. And on the basis of that, then you can discuss other things that may arise. So that was part of the motivation to use this class of approaches that allows us to have these two-way communications with experts in the field. There are, of course, many other techniques that you can use, but we believe that considering the overlap between possibility to discuss and our expertise, that was a very good start to give it a go.
Thank you for your answer.
Thanks for the question.
Oh, yeah, Alexei Ignatenko.
Yeah, good day. Talking about game theory, also, there is a paradox called Brace paradox. Maybe you heard about this. It's like application of game theory to transport problem. So my question is, have you ever experienced it in your simulations? If you don't know, brace paradox is when you create a new rod in wrong place. I mean, very good rod, yeah, and everyone start to use it, so the delay for everyone became bigger.
Yeah, it is. That's a very good question. Actually, it's something that we don't observe much in when you are just dealing. Well, just dealing when you are dealing with the optimization of traffic lights. But we have seen a lot of that when in some of the work that we have done in traffic distribution. So where you are basically these vehicles, you assume that you can communicate with them, and you start moving a number of vehicles on a different roads, then a main one becomes free and all of them are again through that, which is blocked again. And so you have this flipping of the loads between different alternative ways. And so, yeah, definitely that is something that can happen. The way in which we dealt with it was by including penalties and by including a kind of not exactly a risk adverse policy, but the fact that if you are moving away from what has been given to you, or if you're moving away from what initially we tell you, you are paying a small penalty, even if the other road seems to be much better at the moment. And in this way, there was a kind of mitigation. It's not a very smart or particularly elegant solution, but it was a solution that seems to be working for us.
Oh, no, thank you. In a small other question. Now every driver has this, application that recommends him the best way. So, and I believe that this system becomes more unstable if, for example, everyone get advised to go on the one road because it's like free, and when they came here, it's not free anymore. So, did you include this in your simulations? I mean, this information delay, which are right now very small, about the traffic situation.
That kind of behavior, particularly when you use Google Maps, for instance, is quite apparent. And the issue there is that you are dealing in a very distributed multi-agent way. So the agents do not communicate with each other, and there is a centralized system which is telling the agents where to go. And under these scenarios, as soon as there is a road that seems to be better, all of them are told immediately to go there, and you create a jam on that way. But if you take a centralized perspective, you are in a much better position to tell the different vehicles where to go and to distribute the traffic, knowing how many vehicles will go in which way. Of course, you can have issues if vehicles are not following your instructions, or if not, the vehicles are able to follow it. But you can mitigate these load balancing problems in this way.
Okay, thank you.
Thank you very much.
More questions? Okay. So thanks, Mara. Well, almost on time.
Wonderful. Thank you very much. It has been, I hope it has been great for you and it wasn't too boring. It has been definitely wonderful for me.
Yeah, it was just excellent. I enjoyed it. Hopefully, all the gang who was online. Oh, Natalia, say hello to Maura.
Sorry, I'm not alone. Hi, Maura. I'm not alone.
Hello. No problem at all.
I listened also. It was very interesting. Yes, just like.
Very
really
insightful, and for me it was even retrospective. Enjoyed it very much. Thanks a lot.
Thank you very much.
Very good work. I'm
Thank
looking
you.
forward to putting your picture in the middle of the dinner table today.
I'm looking forward to enjoy your dinner from a picture. Thank you very much.
Thanks a lot. This completes our today's festive session.